It's Anirudh Krishna from Stanford University who's going to be talking about hierarchical quantum memories.
Thanks, Nick. Hi, everyone. I'm so excited to be here at my favorite conference where it's good to meet old friends, but also to be able to get into deep conversations with almost everybody. Thanks for fighting jet lag and coming to my talk, and a big thank you to the organizers for giving me the chance to speak here today. I'm going to be telling you about some work that I've done with Chris Pattison, who's a PhD student at Caltech, and somewhere in the audience, and John Fresco. So the objective here is to describe to you a construction of an efficient quantum memory using quantum LDPC codes. And I am not going to be interested in performing fault-tolerant gates, but we will need to be able to perform some encoded gates on surface codes, and I'll get to this. My talk is going to proceed in two stages. In the first pass, I'm going to give you a high-level overview to motivate the big ideas and give you a high-level overview. And this is important because the paper ended up being a lot longer than I'd originally imagined. But the core idea is very simple, and I think I can get this across pretty easily. In the second pass, I will return, having set up this scaffolding. I will then piece together details. And so this deep dive, I will describe how we bring together a lot of ideas to perform explicit constructions. And this is going to involve both asymptotic ideas, but also explicit constructive details that I hope will be of use outside of this specific construction. So I'm going to begin with a high-level overview and some boilerplate information. Given an NKD quantum error-correcting code Q, it's specified by some set of commuting Pauli operators. To actually be able to perform error correction, we need to specify a syndrome extraction circuit. So you're given some code state psi. It's afflicted by some error E. And what we're going to do is perform some Clifford circuit U. Whoops, it's not aligned. And this circuit U is going to take, in addition to the input state, is also going to take some ancilla states here indicated in plus. And if there is an error, it's going to be detected by these syndrome measurements. So a syndrome extraction circuit, whether or not it's efficient, we're going to gauge using three metrics. One, the width, which is the total number of qubits that this circuit needs. Two, the depth, which is the total number of time steps for which the circuit is running. And finally, the probability of failure, the probability of logical failure, which in this case, I've denoted P sub Q. Q is the code. P sub Q can depend on a lot of parameters. It can depend on the code that we've chosen. It could depend on the syndrome extraction circuit. And I'm going to be interested in studying this function as it depends on the size of the code in our code family. So the specific class of codes I'm going to be talking to you about are called low-density parity check codes. And these are codes for which every data qubit only affects a constant number of syndrome bits, and every syndrome bit only depends on a constant number of data qubits. And the idea in circuit form, which is the way that I'm presenting things here, the idea in circuit form is that every qubit, as it's only involved in a constant number of 2-qubit gates, this is going to minimize the depth required to perform the syndrome extraction. And if we were to use a single ancilla bit for performing our syndrome measurements, then we are also using a total number of qubits that's proportional to the data qubits that we've started with. So the name of the game here is to try and minimize the width of the circuit and the depth of the circuit while still maintaining the largest amount of error suppression possible. And this is going to be a function of the code. The performance of the syndrome extraction circuit, how much it costs versus how well it protects your information. It depends on the specific code family we've chosen. And furthermore, even after we've chosen a code, the syndrome extraction circuit itself is not unique, and the probability of failure can depend on the specifics of your syndrome extraction circuit. For LDPC codes in general, however, we can make some pretty broad claims, namely that these codes have a threshold. And what that means, for the sake of this, this cartoon picture that I'm going to be presenting now, you can imagine that every qubit is afflicted by IID Pauli errors with some probability P physical. And LDPC codes can be endowed with a threshold, meaning that for some physical error probability Q physical, if P is less than Q, then the probability of any logical failure falls exponentially. And this is what makes these sorts of codes so appealing. So our favorite code, the one we all know and love, is the simple surface code. In an L by L surface code, it's got n qubits. It encodes it's got n physical qubit. It encodes a single qubit, and it's got distance d. And what that amounts to, as far as our syndrome extraction circuit goes, is that we've got a circuit with depth 1, ignoring having to repeat syndrome extraction with noisy syndromes. It's got depth 1. The probability of failure falls exponentially in L, which is the side length of your surface code. And the total number of qubits that you need is n times polylog n to encode some k qubits. Or maybe I should have said k times polylog k. However, the promise with LDPC codes is that under certain constraints, if something happens, and I'll tell you what that is, there exist codes for which you can encode with a constant rate, meaning k is proportional to n, and the distance of the code scales as some polynomial function in n. And what this allows is potentially an improvement at the pace at which we can suppress logical errors. And in addition, it can also do so simultaneously using fewer physical qubits. So that's the broad advertisement of quantum LDPC codes. But of course, I've alluded to something here. Something needs to hold, something needs to be true for you to be able to construct such syndrome extraction circuits. And what that something is, I should have mentioned here that this parameter delta, it specifies how the distance depends on the parameter n. And delta is some number between 1/2 and 1, or can be chosen to be a number between 1/2 and 1. Okay. So what do we need to be able to construct quantum LDPC codes? We need to be able to perform reliable 2-qubit gates. If we were to lay qubits out in 2D, we need to be able to perform reliable 2-qubit gates on gates that are not on qubits that are not necessarily adjacent to each other. One of my favorite papers, or two of my favorite papers, are by Bravi and Terhal and by Bravi, Poulan, and Terhal. I return to these papers regularly, and what they say is that if you're constrained by geometric locality, then your code parameters can't be very good. In particular, they show that there is a very sharp trade-off between the number of encoded qubits and the distance of your error-correcting code. And the surface code basically saturates this bound. So it's up to constants, this is as good as you can possibly hope to do. Later, Noiden and I had shown that if we flip this question, if we were to ask, there's some target code parameters that I'd like to achieve, how much non-locality is that going to require? We showed that if you have an NKD code with constant rate and distance d, then you're going to need a lot of long-range connectivity. In an L by L grid, you're going to have at least a constant fraction of your qubits connected to other qubits that are basically distance L away. So this is about as bad as you could possibly get. And soon after, there was this beautiful paper by Nicolas Delfosse, Michael Beverland, and Maxime Tremblay, where they showed that if you were to, again, cast things in this circuit picture in terms of a syndrome extraction circuit, they demonstrated the following trade-off. This is simply to build up the amount of entanglement to construct a constant rate LDPC code, you're going to have to put in a lot of effort. Namely, the depth of the circuit is lower bounded. It's lower bounded as a function of the total number of qubits that you're using, as well as the number n of data qubits. Why is this a problem? This is a problem because they also then showed some numerical evidence that in this constrained scenario where you're only using local nearest neighbor gates, then you might not even have a threshold. As you increase the code size for a fixed physical failure rate, the probability of logical failure only gets worse. Unlike in the setting where you have all-to-all connectivity, where as you increase the code size, it displays threshold behavior. So how do we overcome this? We overcome this by using the oldest trick in the book, namely code concatenation. Okay, so let's return to this trade-off and what it says. And let's intuit how this might work. Okay, so we have this L by L grid, right? And we've already mentioned that most of our qubits have to, a constant fraction of our qubits have to talk to qubits that are potentially on the other side of the lattice. How are we going to perform the circuit to saturate this bound? Let's suppose that there's one circuit here and another circuit there, 2 corners. And what we could do is simply swap. And once the two qubits that we want to perform gates on are right by each other, we can perform a C0 gate and then swap back. Okay? So in an L by L grid, if I need to travel L distance, then clearly the depth of the circuit is going to be lower bounded. So that's one way to intuit where this is coming from. Okay? But herein also lies the problem. If every swap gate is failing at some probability p physical, then this virtual C0 gate that I performed by swapping C0 and then unswapping has a very large failure rate. And in fact, this failure rate grows with the size of your code. The total failure rate scales as L times p physical, which is some polynomial function of the total number of qubits you're using. And this is a problem because the threshold theorems that we know and love require that all of your gates fail at some constant probability. In this sort of setting, then, you're no longer guaranteed a threshold. So instead, what we're going to do is encode each of our physical qubits into a surface code. And what this is going to allow us to do is, as the qubits are moving from one spot to another, we're going to be able to protect it using just the surface code. And the surface code itself only requires local gates. So in the setting where we're constrained to use only local gates, and we encode every physical qubit in our LDPC code into a small surface code, we can protect qubits as they move from one point to another. And what this then implies is that if we squint, forget about the inner surface code and just look at the outer level LDPC code, the total failure rate is going to scale still as square root n. The distance that you need to move is still L, but the failure rate now is the failure rate for performing logical operations on your surface code. And as we mentioned earlier, the surface code does have a threshold. You can encode a single qubit, and it has a threshold. And the rate of logical failure falls exponentially. So here's this thing that's growing polynomially in n. Here's this thing that's growing here's this thing that's falling exponentially in L. If you let L be log n, then you can make the probability of your C0 failing an arbitrarily small constant. And that's it. That's the idea. And from this, everything else follows. So what is the class of codes that we construct? We call these hierarchical codes. It's an NKD family. And here I'm using capital N to index every element of this family. So you do pay a price. Because you do pay a price for locality, I mean. And this price is not terrible. Ideally, you would have liked to start with you would have liked to end up with a constant rate code. Unfortunately, this is not possible. So asymptotically, the rate is vanishing, but very slowly. You're able to encode a number of qubits that grows with the system size. Now, second, having concatenated, the code is no longer strictly LDPC. Because the inner code is growing, the outer code is strictly no longer LDPC. The stabilizers have weight log n. However, what we're going to show is that you can construct a syndrome extraction circuit that only ever uses local measurements and local gates. And most importantly, on the asymptotic side, we showed that this code has a threshold. So for small enough physical error rates p-phys, the logical failure rate is going to fall super polynomially. So again, if you're used to seeing a typical threshold proof, you might notice this extra log n factor that is slowing things down. So the probability of logical failure is not falling as fast as it might have had there been no geometric locality constraint. So the log n here and the log n there is the price that you pay for having an entirely geometrically local circuit. Okay? With that said, this function is still super polynomial. And so for practical purposes, at least this doesn't prevent you from moving towards practice. Okay? So with that, I move to the second part of my talk, and we'll start adding details to this high-level overview. Okay? So I'm going to start by considering the circuit for the outer code. So this is just the LDPC code, and we know that qubits might be far apart. Qubits that need to interact via a C0 gate are far apart. And in the previous cartoon that I presented, I just mentioned that I considered a single pair. I considered one qubit here and another qubit there, and they're connected by some virtual C0. But really, what you need is a way to move all of these qubits in parallel. You'd like to minimize the amount of time that they're just sitting around doing nothing. And we need ways to avoid collisions as you permute multiple qubits at once. So what might happen is if you've got two qubits, V1 and V2, and V3 and V4, both of them need to interact via C0, but they're not far away. So here's what the physical embedding might look like. V1 maps to W1, V2 maps to W2, and so on. And the way that we're going to perform gates, as I said, is swap, perform a C0, and then swap back. And in this simple cartoon, you can see that if W1 has occupied this little intermediate spot where I can perform a C0, W3 and W4 cannot interact, so there's a collision. So I need to be able to figure out how to perform all of these permutations in parallel, and the way that I'm going to do so is by expressing this as what's called a permutation routing task. And it turns out that you can do so by using this very old algorithm. It appeared in, I think, the 90s by Anixtein and Baumslag. We were able to build on this algorithm for performing permutation routing and move things in parallel. And I want to stress that this method for circuit construction, or this algorithm that's at the core of constructing our syndrome extraction circuit, is not merely an asymptotic tool. This is from an explicit implementation, and we can also tell you exactly how much time it runs in. These are not merely n goes to infinity claims. Looking into the future, we've also generalized this method for constructing syndrome extraction circuits in a specific way. Namely, it may be possible that in the near future, perhaps you can't get any qubit to talk to any other qubit in an L by L grid, but you may at least be able to get the qubits that are not immediate neighbors to talk to each other. So our algorithm allows for such a generalization. If you've got a range R for your swap gates, so rather than having to move nearest neighbor, if your swap gate can allow your qubit to jump R units at once, then we can still show that you obtain a sparse graph so that any permutation can be performed in depth L over R. So as the non-locality of your swap gates increases, the depth of the circuit decreases. So thinking back to this bound by Delphos, Beverlin, and Tremblay, this is saying that as your locality constraint is decreasing, you can perform circuits more efficiently. So in this specific setting, what we're going to do is arrange all of our physical qubits for the outer code in a bilayer architecture. And at every time step, a data qubit is going to be paired with a syndrome qubit, one in each layer. And at every time step, a data qubit is going to be paired with a syndrome qubit and then routed using this permutation routing algorithm. And since we're working with an LDPC code, there's in a constant number of time steps, every qubit is only going to have to interact with a constant number of data qubits. You can do this in a constant number of time steps, where every time step then involves some number of routing primitives. Okay, so with this, I can then zoom in and talk about the circuit, the syndrome extraction circuit, as it applies to the inner code. So here too, we're going to be continuing to use a bilayer architecture, and now I can motivate why I did this. So in this bilayer architecture, since every physical qubit in my LDPC code is blown up into one surface code, if I want to perform a C0 between a syndrome qubit in the top layer and a data qubit in the bottom layer, I can do so transversely. And so I can perform transversal C0 between the two copies of surface code, and that's going to implement a logical C0. Okay, so this is where we need to start thinking about, even though we're only interested in constructing quantum memories, we still have to think about performing fault-tolerant gates on the inner code, and allowing these gates to be transversal automatically means that they're going to be fault-tolerant. But in addition now, I also need to tell you how to perform swap gates on these little patches, on these tiles. And I'm not going to have time to get into that. I have slides in case we have time at the very end. But we have new techniques for performing swap gates in parallel. So I can tell you how to swap these tiles in a manner that behaves well with the previous algorithms by Annigstein and Baumschlag that I talked about. So what is this bias? It biases the following. Ultimately, we end up with a syndrome extraction circuit for the hierarchical code, such that it still has constant overhead, or really the total number of physical qubits that we're using is proportional to n. Furthermore, the depth of the circuit scales as square root times n over r. Okay? So if you're not interested in the setting where you have non-local gates, you can let r equals 1 and everything still holds. There's some things that change that I need to take into account as I'm performing this concatenation, namely that there's a set of active qubits in the middle, and there's an extra set of qubits that are not going to be used at any given time step. And this buffer space, all of the memory stuff is going to be happening here, and these could be used as extra scratch space. And this is going to be necessary for implementing our logical swap gates. But even with that, the total overhead is still only going to grow by a constant factor. Okay. So what noise model are we working with? We are working with a locally decaying noise model. And what that means is that we allow for very general sorts of errors to occur. You can have this sort of error model can allow for correlated errors and helps us understand also errors that can spread inside circuits. And what it means is that the only constraint on the errors that occur are that the probability of an error is inversely proportional to its size. So the larger the error, the less likely it is to occur. But subject to that constraint, anything can happen. And to get to the asymptotic portion of our proof, we're building on a result by Gottesman, where he's able to show that there exists a threshold if the error rate per round of syndrome extraction remains a constant. Now, this might seem trivial when you're dealing with an LDPC code that's not constrained by geometric locality. You can perform the circuit in constant depth. So the error rate per round is also then a constant. However, with swap gates and having to perform permutation routing, the depth of the circuit is growing. So at the outset, it might not be immediately obvious that the error rate per round of syndrome extraction is constant. But thanks to the structure of the syndrome extraction circuit, so here I have a little gadget that we use to measure X-type syndromes. And what we find is that because the C0 gates are only going in one direction, it only allows for Z errors to flow back into the ancilla qubits and X errors flow down from ancilla to data. So between rounds, you can't have an X error flow down from one ancilla qubit and then flow back up. So there's restricted ways that errors can flow within these syndrome extraction circuits, and that allows us to prove, to show that the error rate per round of syndrome extraction is indeed a constant. This also allows us to account for instances where we do have errors on syndrome qubits. We can show that the error on all of the qubits, not just the data qubits, but on all of the qubits is constant per round. And what we find is that the parameter that describes the error rate per round scales 1 as the depth of the circuit, and second as in proportion to the physical failure probability. And this quantity is what is going to be the logical failure rate for the inner surface code. So we had this intuitive explanation for something that when you swap, it's going to be L times the probability of failure for each swap. And this allows us to put the same statement on more formal footing. Okay. And finally, that allows us to prove that these codes are going to have a threshold. So with all of this work, you might be asking, if you are indeed constrained by geometric locality, why did you go through all of this song and dance? Why don't you do something simpler? Namely, if you're using all of these extra resources anyway, why not just put that into building better surface codes? Okay? So in this specific context, suppose we're using a total of m qubits. I'm going to be defining what's called a basic encoding that uses m qubits. And it's just the simple code that has k patches of surface code, each of them of size L by L. And the question that we'd like to ask is, if I wish to achieve a logical failure rate that's better than that of my LDPC code, then how large does m have to be with respect to n? In other words, how do we quantify this in terms of these circuit parameters? We find that it's always going to be true that the depth of the circuit that is working with a basic encoding is going to be polynomially larger than the depth of merely the LDPC code. And furthermore, assuming that delta is greater than 1/2, delta here, remember, parameterizes the distance of your LDPC code. The depth of the basic encoding is also going to be polynomially larger than the depth of your hierarchical code. And the second fact only applies, I should say, when we have a single-shot LDPC code. But if this object were constructible, then we're going to find that in the asymptotic setting, the hierarchical memory outperforms the surface code on both fronts, on both the width and the depth for a fixed target logical failure rate. Okay, so the other thing that I wanted to highlight here is that when we were working on this, John mentioned to us, okay, asymptotically, some of this stuff is obvious, but when we look at the numbers, is it going to make us cry? And I'm going to present the numbers to you, and you can decide for yourself if you want to cry. So what we're doing here is considering the instance where n is equal to m. In other words, the total number of qubits that the hierarchical memory is using is equal to the total number of qubits that the basic encoding is using. And we're looking for the crossover point, namely, as we reduce the gate error rate, at what point does the hierarchical memory start to perform better than merely using basic encoding? I should emphasize that these are not numerical simulations. These are more back-of-the-envelope type calculations that are assisted by a computer. So you might notice that the logical failure rates are extremely low, and if you start to have questions about how we sampled to get these things, we didn't. These are numerical estimates, and I'll talk about what goes into this now. So to make these sorts of estimates, what we're doing is that we have assumptions on our noise model at various levels. On level 0, assuming that all of our gates fail with some probability p, and I'll return to this assumption in a sec. Second, on level 1, we're assuming that the surface code has an error rate that falls exponentially below some threshold. We're assuming that the threshold here is roughly 10 to the minus 2, and below that threshold, it's falling exponentially as follows. And furthermore, that the logical failure rate, so this is just for memory, but then while we're performing our swap gates, I'm assuming that the logical failure rate falls exponentially with the amount of time that you're performing, that you need to route it from one point to another. Okay? And finally, in level 2 for the LDPC code, we're assuming that the logical failure rate for the code, in this case, we're assuming that we're working with a hypergraph product code. We're assuming that the threshold circuit threshold is like roughly 10 to the minus 3, and it too is falling exponentially below this threshold as a function of the distance. And I will return to this factor of 10 shortly. Okay. And the specific code that we're using is enormous. Okay, it's the number of qubits is in the millions, and the reason that we do this is because we were originally working with some worst-case assumptions that your code is going to be maximally plagued by what are called hook errors that we heard about this morning, and if we assume that the distance of the code, the effective distance in your syndrome extraction circuit, is going to fall in proportion to the degree, then we need to start off with a very large distance so that the effective distance then is manageable. So what we plugged in here into our ansatz is here the effective distance. It's roughly the actual distance divided by a factor that we think is going to affect syndrome extraction. Okay. So with that, with all of this explanation, let's then turn to look at these plots. What we're seeing here is for this fixed hypergraph product code, we're asking what happens if I were to perform this one round of concatenation. I've concatenated with this surface code, and the specific code that I concatenate with is shown here using solid lines. And in contrast, there's a basic encoding, which uses a lattice of size dm, whereas the hierarchical encoding uses a surface code of size dl. Remember, we can use much larger surface codes because we're saving resources by not performing all of these routing tasks and using an LDPC code. With that, the numbers look quite promising. You know, modulo this extremely large size. Again, that's something I'll return to. The numbers look quite promising. Where does this crossover happen? You can see that the solid line that corresponds to the hierarchical memory crosses the corresponding line of the same color for the surface code at roughly between 10 to the minus 3 and 10 to the minus 5. So it isn't something absurd. For a first pass back of the envelope style calculation, it isn't like 10 to the minus 20 or 10 to the minus 50 or something. It's between 10 to the minus 2 and 10 to the minus 5. These different colors represent different sizes and choices for our hierarchical code and the basic encoding. So that's the very first plot. The next two plots are instances where we assume that just your swap gates are better, and they fail with a failure probability that's not as bad as the rest of the gates in your circuit. So assuming, for instance, that your swap gates are performed using an entirely different mechanism, you're not using the same coupling mechanism that you use to perform 2-qubit gates, perhaps you're just straight up moving atom traps or something, then these can have very different noise mechanisms, and potentially your swap gates can perform a lot better than your C0 gates. So in the very first plot here, it's the same story, except the swap gates alone have 10x better fidelity, and in the rightmost plot, they have a 100x better fidelity. So the crossover point, the logical failure rate for this crossover point starts to increase, and it also starts to move slightly left. So these are all positive signs if we want to construct these hierarchical codes. So let's return to some of these numbers because they don't look very promising. Soon after our results, actually not too long ago, there was a paper that showed that hypergraph product codes are not affected by hook errors. So we're certainly not going to have to bake in this level of tolerance into our hypergraph product codes. We can potentially get away with using codes that are much, much smaller. I have 5 minutes, so I have 10 minutes. Yeah, okay. So I can get into some more details then. So I've given myself some buffer room. So let me just summarize the main points that I've made so far, and then I can get into some more details. So the hierarchical code families that I presented are one way to realize the promise of LDPC codes with only nearest neighbor gates. we find that local measurements are sufficient for you to be able to construct these syndrome extraction circuits. There is a cost to locality. The rate is vanishing, and also there's sub-exponential error suppression. But these numbers are still positive, and it's good enough for you to be able to construct circuits in practice. And lastly, we also have explicit circuits for you to perform permutation routings if you do have long-range gates. So in the future, I expect the performance of these codes and these numerical estimates to look a whole lot better when the decoders for the outer code and the inner code can interact with each other. So in these plots, we had this ansatz where we plugged in various parameters for the logical error rate scaling for both the inner surface code and the outer code. But there's more information here that we're not exploiting. Namely, when the inner surface code fails, we might be able to get more information as to what sort of failure occurred, and that can then inform the decoder for your LDPC code. And with this sort of asymmetry that's built into LDPC codes, decoders, they can perform a whole lot better. And this too can also then significantly improve the logical error rates. In fact, Chris is currently working on something like this with a student, and the numbers are looking extremely promising. And of course, the long-term next step would be to ask how we can perform fault-tolerant gates using this setup. So with that, I can talk about some of these techniques that we've introduced for performing swap gates between tiles. Here's a high-level overview. So what we've got is a side view on our bilayer architecture. And here's how it's going to work. In this little toy example, I'm going to demonstrate that using only local moves, I'm able to swap the tiles A2 and A3. Okay? So we've got A1, A2, A3, A4. These are 4 tiles. There's some buffer space on either end, as I mentioned earlier. And when I'm done, I'm going to have A3 and A2 having exchanged places. So how is this going to work? In your bilayer architecture, you're going to start by swapping alternate rows. You can then perform a walk operation. So we call this the walk primitive, where every tile moves one unit to the left. You then perform, again, a local move between layers, another walk layer, and between layers. So in every step, what you're doing is either local moves between the top layer and the bottom layer, or you're performing local operations within a layer. All of these operations can be performed in parallel, and what that leaves you with is these 2 tiles having swapped places. And we're going to use this trick when we're swapping surface code patches as well. Each of these operations is going to be initialized as follows. When I want to perform this exchange between one layer and another, I'm going to begin with 2 surface code patches that are staggered. And what this allows us to do is exchange a data qubit in one layer with an ancilla qubit in the other layer. That way, this operation remains inherently fault tolerant. So there's this one stagger operation that's required for performing operations between layers, and then you can unstagger them when you need to swap. In the second, the walking primitive, where you need to swap inside a layer, here too you can exchange the data qubits and the ancilla qubits, and this allows you to perform these operations in parallel, right? So the data qubits are the important piece. That's where we store our information. And then you perform the swap. The roles of data qubits and ancilla qubits are exchanged, and then you can use the new syndrome qubits to perform measurements and one more round of error correction. So by allowing for this interplay between what functions as syndrome qubit and what functions as data qubit, we're able to perform these 2 primitives that we need, one between layers and 2 within a layer, in order to compose this global swap operation. this slide is a cartoon. It's meant to represent this previous like side view that I'd showed you, where you can do these operations successively between layers, within a layer, between layers, and that's going to then allow you to perform these swap operations in parallel for permutation routing tasks. The other thing that I didn't highlight, but may be of use elsewhere, is when we are considering using an inner surface code for other uses. Namely, so if we were to look at these hook errors more carefully, what they are is when there's an error on our ancilla qubits and then it flows down to our data qubits. And this reduces the performance of your code because one error in your ancilla qubit can multiply and spread to multiple data qubits. So the way that we had proposed tackling this is by using an asymmetric LDPC code. We recall that it's only the X-type errors that flow down and become Z errors in the case of these gadgets. So by making one side much longer than the other, you make it much more likely for the ancilla qubit to fail and then propagate that error down to your data qubits. So you're going to elongate both your syndrome qubits as well as your data qubits in a way that errors here that could flow up and the errors here that could flow down are both exponentially suppressed. Hopefully this is going to be of use even in instances where you don't have to worry about hook errors. This allows you to dynamically create a bias. If we were to return to the plots that I showed earlier, where we ask for these sorts of back-of-the-envelope style calculations, which performs better, the hierarchical memory or the basic encoding? The crossover now looks a whole lot more favorable. The logical error rate at which these sorts of crossovers happen has moved up significantly. And furthermore, we also find that we're able to get away with codes that are a lot smaller. So rather than 1 million, you can get away with using a code that uses only 300,000 qubits. But anyway, this is just meant to be an illustration of the fact that when you are able to dynamically engineer a bias, you can get away with much lower space overhead. And lastly, I wanted to mention that in instances that you're dealing with burst errors, where a large patch of qubits locally is taken out by, say, stray rays from the sun, this is fine because each of our local patches here is a surface code. So rather than having one large code that you might have to grow to increase the distance as you would if you were using only a surface code, the fact that one little patch of your surface code is deleted means that it can be treated as an erasure for the LDPC code, the outer level code. So this is also going to allow you to deal with burst errors by performing encoding in this manner. And with that, I'm done. And I'll take questions.
To begin with, there's a question from online we might start with while people in the room work out questions and microphones. The first question is, are the rate and distance costs you pay for keeping things geometrically local optimal? Is this the best we can do?
That's a great question. I don't know, but I suspect they are.
Hi, thanks for the very nice talk. I was wondering how you included the overhead of fault-tolerant extracting the syndromes of the outer LDPC code in your estimates.
What do you mean?
Don't you have to extract the syndromes of the outer LDPC code
Yes.
fault-tolerantly?
Yes.
And that overhead is also included in all your simulations?
Yes. Yes. So we have some number of outer syndrome qubits, and those syndrome qubits are also going to be patches of surface code. So everything in the outer in the syndrome extraction circuit for the outer code, all of the qubits are going to be replaced by surface code tiles. Does that help? Sure.
Have you looked at the additional overhead or impact of using a lattice surgery-based approach to implementing this hierarchical memory as opposed to the bilayer approach that you've described here?
Right. So as far as the asymptotics go, it doesn't affect the story. You still will have a threshold, and you don't need to consider this bilayer architecture specifically. Any way of performing logical gates on your surface code will work. As far as the numerical estimates go, no, we haven't. And that's something that I'd like to learn more about. Slightly worse? Okay. There you go, slightly worse.
Hi, thank you for the nice talk. I have a question about your proposal of bilayer architecture.
Yeah.
At that point, you introduced using 2 layers and some non-trivial way of performing swap, but you could have suggested using only a fully single chip.
One layer, yeah.
Yeah, with a sufficient amount of auxiliary regions.
Yeah.
Do you prefer using is there some reason that you suggest 2 layers? You prefer 2 layers
Yeah, as
rather than full 1 layer?
Yeah. So as the reason I mentioned for considering these bilayer architectures is because it allows us to perform logical gates in a transversal manner, namely the C-NOT gates. But you could perform all of your gates using lattice surgery, and it still ought to work. And you can then put everything down in a single layer. You wouldn't need to.
Okay, yeah, so you want to perform everything transversely.
Wrap it up there and just thank the speaker again.